Hi, everybody. Welcome to our second episode of our open source system breakdown. And where I'm super excited to get Simon Shillaker to talk about Faasm. And this will be a pretty interesting talk given how much interesting level of system level work that I think Simon has done. There's an ATC paper, I think, as well. And so we'll be, we have a lot more details we can share. But yeah, welcome to our show.
Pleasure.
Yeah, so let's get right to it. Tell us who you are and what got you into even start to do this in the first place.
Yeah, so I used to be a professional developer. Then I started a tech startup with a friend of mine where I was the CTO. And, like all startups in the last kind of 10 years or so, it started off a bit of a mishmash and then just became everything on AWS. And so, you start then having to justify why you wouldn't use the AWS version of X product, and because it's just so much easier. And serverless kept kind of cropping up in there. It's used a lot in a lot of systems to glue bits together. You have this thing happen, and then a serverless function gets triggered, and it writes something to a database, etc. And what serverless is now kind of works well for that, but there's this broader sort of philosophy of serverless, I guess, which is actually the natural conclusion of sort of increasing levels of abstraction in cloud computing. I guess cloud computing is all about abstracting the user away from all the difficult stuff and just letting them focus on what they're doing to add value to whatever part of organization they're in. And so with serverless, the idea is that I just write some code and I give that to you as a provider. You execute it when I need it, however often I need it, at what scale, and you bill me for what I use. And so I kind of saw that promise of serverless, but then the reality of what serverless is today, which I don't want to sort of criticize and say that it's not good. It's very good for the thing that it does, but what it's essentially sort of containers as a service, in that I give you a function, a stateless function. You execute it for me on demand. That will eventually be in a container somewhere. And I can't guarantee the level of parallelism that I get. I can't actually guarantee how quickly you'll do it for me. I can't share state between my functions. And the functions themselves can't discover each other and sort of send messages between them. And so I wanted to transition away from being a CTO back to being more technical. And then I talked to my supervisor about doing a PhD on serverless computing on exactly this topic. And so then I did this PhD, and this is kind of the result of it. I've almost finished the PhD. And so it's kind of rounding off quite nicely now. There's a few solid features there that are now done. The main problems that we've focused on, the first one was the isolation problem, which I will explain. So if I'm a provider of serverless computing, I'm basically opening my doors to the world, and I'm saying, like, everyone just give me your code. You don't have to tell me even how often you want to execute it in advance. You're just going to throw requests at me, and I'm going to scale out to meet that. And that makes the provider's job really difficult, because they can't provision anything up front. They need to be able to do very fine-grained scaling. Otherwise, they're going to be provisioning big VMs for every 100 millisecond request, and it's going to get super expensive. The problem is an operating system isn't really built to be a multi-tenant execution environment. And so with serverless, you're getting to a uniquely small level of task, and the smallest reliable isolation mechanism we have is probably a container that will give us the level of guarantees that we need to be confident enough to run people on the same operating system. Even that, I think you have to add something like, there's a thing called gvisor, which is sort of goes in between a container and an operating system to strengthen the isolation. when I started my PhD, that was basically state of the art. Since then, Amazon have created Firecracker, which is a micro VM, and that does a really good job. However, all of these forms of isolation, almost by definition, don't permit you to share anything between those isolated units. And so they're also quite... I really don't like using the word heavyweight because it's so undefined. It's heavyweight compared to what or in what scenario. But one of the really common problems that people see with serverless is the cold start problem, which is where I have to wait, 100 milliseconds, a second for my thing to come up. And that's because containers take that long to start up. And so we sort of thought, what isolation mechanism would be better suited to a serverless environment that would be low overhead, but also perhaps permit us to share things between stuff on the same host. The other problem you get with serverless, because everything has to be stateless at the moment, all state has to be held in some external storage somewhere. And that means that even if I have two functions on the same host that are working on the same bit of data, I have to load two copies of that onto the same host rather than process it in memory. So anyway, we sort of went around the houses thinking about multi-tenant runtimes and then stumbled on WebAssembly. And so this was kind of 4 years ago, maybe, when WebAssembly wasn't so well developed as it is now as an isolation mechanism outside of a browser. But WebAssembly is really nice in that it's super lightweight for what it gives you. I don't want to say that it gives you the same thing as a container because it doesn't. It gives you memory safety and control flow integrity. But that's quite an important part of the isolation that you need for serverless. In addition to that, you need to make sure things have fair access to resources on the host. And then you also need to make sure that access to those things on the host is also secure. Because WebAssembly doesn't provide you with that. Since I started my PhD, there's this new thing called the WebAssembly System Interface, or WASI. And that basically does what I'm talking about there. It lets you execute things in WebAssembly, but also gives you it gives you isolated access to the underlying file system calls, networking system calls. It doesn't deal with fair access to those resources. You still have to do that. If I've got one host that's hogging the network, one function that's hogging the network on the host, WASI won't make sure that's fair. Anyway, so we created, that's where the sort of building block of Faasm came from, the idea of isolating serverless functions with WebAssembly to get the high performance part.
Got it.
So then, sorry.
I think you actually talked quite a lot in the intro, because I think most of our listeners are probably technical, may not understand completely all the isolations and nuances. But I guess maybe in my summary, right now the best of our state of art is Kubernetes, right? Like we run everything on containers, and they all run in VMs. We don't know where they're gonna be, but if you really want to able to share resources, that's not extra copies at every host, like you mentioned, right? Today with Kubernetes, you basically have to pin them on the same host, create a shared drive, right?
Yeah.
Share a mountable folder, basically, and do all that yourself. And all the operators are doing that for whatever reason, performance reasons. And so I think the inspiration you have, I guess it sounds like, is that you want to make serverless programmable. It's the same way, but still have fast performance with data intensive or data with stuff that needs to be stateful, I guess. And how do I deal with that as simple as possible, where I don't have to copy data, where I can share resources? But it sounds like data is the biggest state is the biggest question. How you need to solve this, right?
Yeah, I guess you can start, if you take an even bigger step back from the pool that I just dove into, you could basically say, what can I actually run on serverless nowadays? And this was the same thing I was seeing in my job. I was thinking, okay, I can run these asynchronous downstream processing functions, but if I want to take that idea of serverless further, and let's say I'm running any like machine learning training, some parallel application where I need lots of data and lots of parallelism, but I'm only going to run it every now and again. Serverless in theory is great for that, like if it fulfills its promise of just being compute on demand. However, because of this enforced statelessness and lack of sharing, the performance overhead of me moving my data all around all these functions becomes prohibitive. But then also the programming model that serverless enforces now of like stateless chunks, of which you're not sure how many there will be, it's quite difficult to write a parallel application that actually works for that. And it certainly doesn't fit anything I would recognize now library-wise. I can't just use my whatever TensorFlow or scientific programming framework and just say run on serverless, because it's kind of not built for that, even though it could be. I really want to caveat all this stuff by saying like being a serverless provider is really, really difficult, which is why all these restrictions exist. It's a really hard problem to solve.
Yeah, got it. And I think we already touched on like the evolution, right? We're in a WebAssembly sort of like, I guess, the start a revolution of WebAssembly, where we want to start to bring it to lots of different places, lots of players in the space. WASI is probably one of the most exciting part of this, like you mentioned, that's doing isolation. So let's dive into the Faasm and the fabrics a little bit more, because I think you touched on the original intention is to be able to do more than what WASI is, right? WASI does this sort of like syscall, so this is kind of like this what syscomp is doing in a typical host Linux fashion. But now you want to say like I want better isolations, and it's a tricky problem because isolations typically, even back in the VM days, they don't even do it that well. Even on networking, right? They don't even actually protect that much. You could get really bad hosts, stragglers. That's why it all happens.
Yeah.
And I guess, so talk about what kind of isolations you're talking about, because there's many kinds, right? There's the resources, obviously, and you're actually talking about fault isolation as well. Like, what is the isolation you're trying to enforce, and why does it matter? Like, why would it actually matters to the end user at some point?
Yeah. Well, so in serverless, I guess there's 3 levels of isolation. One is between tenants. So like you and I are both operating on the same serverless platform. I don't even want to know you're there. I shouldn't know anything about you. I shouldn't be affected by you in any way. Then there's the isolation between my applications, my serverless applications. And then there's the isolation between the different functions of one application. So this it gets weaker as you go down. And actually, I don't want that much isolation between the different functions of my application. I want them to share quite a lot of stuff, probably. And it's going to make it more performant if they do. But I still want to have a platform where I'm completely isolated from my fellow tenants. I guess the thing with serverless that's a bit of a get out of jail free card as well is that the kind of applications I'm executing are not arbitrary POSIX applications that might use the full operating system. It's probably going to be something that does some computation and maybe queries a database or operates on some in-memory data. Might not need a file system, probably don't need any networking, certainly don't need any devices. And it's possible that I might not even need multiprocessing for a lot of these things. So if you think about what a normal operating system does, you can simplify it quite a lot in terms of serverless applications. So then in terms of isolating them, there's those 3 levels. The cross-tenant one is probably the easiest one to think about, because it's like, I as a serverless provider will want to execute 2 serverless tenants on the same machine. So that's like having 2 processors running in your computer. You don't want your browser to mess up your Slack.
Yeah.
If your browser goes nuts, Slack should still run. You should still get a fair crack of the whip. Yeah. And fortunately, operating systems can do that already. Okay, inter-process fairness. Yeah. There's C groups in Linux.
That's right.
Are kind of a plug and play thing. You can say, I'll create a C group for this tenant. I'll add all their threads to that, and then another one for another tenant. And then you're like bingo, they've got fair access to the CPU. Networking as well, use what the operating system gives you. You can manage that.
Yeah.
That's the fairness side of things. But then also I don't want them to be able to be maliciously able to corrupt something. If I've got a buffer overflow error, I don't want that to mess up the operating system for the other tenants. And so this is where a container can give you some pretty good guarantees, I think. Webassembly also gives you those same guarantees. So Webassembly is handling that badly behaved application isolation, making sure that things behave well. And then the rest of the isolation that Faasm provides is also providing the fair access to the resources. So making sure that people can't trample on each other.
Got it. Okay. So I think maybe we should dive into Faasm a little bit, because I think it will probably be more clear what are kind of the resources you're trying to share. And the whole point is that we want to be flexible, right? We don't want to be just isolating everything, because then you cannot do some of the clever things to make it faster, right? For shared resources, this could be memory, IPC stuff. This could be actually files and data that you can actually do stuff. I should assume, right? So maybe let's talk about Faasm. Like, what did you do here? Like, what is the stateful serverless runtime? What does that mean?
Yeah. So this is the bit that I, as the serverless provider, would run. And I would throw the requests coming in from my tenants at this thing. I'd say, like, Tim wants to execute this function, Simon wants to execute this function. The runtime is the thing that provisions resources on a distributed cluster to serve those things. And then it redirects the requests to those resources. And it also makes sure that anything that it wants to share between those things that are executing gets shared and put on the right host.
So it's like a Kubernetes, right? It's like a Kubernetes layer, actually, right?
Yeah, it's kind of, what we wanted to do was avoid reinventing the wheel. So it actually runs on Kubernetes.
Okay.
It's a little bit like Kubernetes will do the auto-scaling part of scaling the actual instances of the Faasm runtime. So each Faasm runtime instance is a pod in Kubernetes. And that's all you need to do. You just need to say, auto-scale these guys up and down, and then they will discover and talk to each other and share the load between them automatically. So that's kind of the layer. It's like, there's another product called Knative. I'm not sure if you're familiar with that. That's sort of a layer on top of this kind of serverless. That adds the scaling down to zero part of serverless on top of Kubernetes, along with other things. And so, what's super counterintuitive is actually Faasm runs as a Knative controlled pod. So the Faasm runtime itself basically will scale down to zero or scale up to meet load. But has its own endpoint for receiving invocations, so that actually each Faasm pod may receive a function call, and it may choose to share it with others. And so this is where Faasm is sort of a distributed system that just works. You install it on your Kubernetes cluster and you start throwing requests at it, and it kind of scales up and down and shares, makes sure that all the data is in the right place, makes sure that the functions are co-located properly, and then makes sure that things remain isolated while they're doing all that.
Got it. Okay. I think I get the gist. I probably what's not so clear is, because I think Knative, I'm not intimately understand it so well, but I know it's like a serverless controller. You can also throw containers for it, and it knows how to quickly execute it with like dealing with co-star problems and stuff like that. That's kind of as much as I know. And you're building on top of that. Are you like replacing the actual executable when it comes like a Docker image only, or you're actually even more, beyond that level?
No, it's actually far from that level. I guess it runs. Knative is still allocating one container per function. So if you have an application made up of 100 functions, you still get one container per function, and you still have to do all the suboptimal stuff I was talking about earlier about storing your data in Excel, and those things can't share anything, even if they're on the same host.
Got it.
The Faasm runtime is also one of those pods, one of those Knative functions.
Yeah.
But actually, each Faasm thing can execute multiple functions.
Oh, okay. I see.
So it's sort of, yeah, and so it's like, you could run it on bare metal as well. You could just have a Faasm runtime running on each host, and then that would do exactly the same thing. That would talk to each other and share data and share functions and things. But like I say, there's a lot of good work out there on doing all the nuts and bolts of serverless
Yeah. I see. Yeah, you don't want to
scaling.
reinvent the wheel.
Yeah, exactly. This is. I didn't want to make yet another serverless platform.
Yeah.
I wanted to kind of build on the state of the art, if possible. And so,
Okay.
yeah.
Okay, so I get it. Just so you have Knative, Kubernetes, Knative, that still works as a serverless platform, but when you want to run Faasm, basically I submit some sort of Faasm request that sort of batches a bunch of potential functions that want to share data to you. Then you can actually figure out how to like distribute it among the available Faasm pods.
Yeah, exactly.
Ideally, some optimistic way to run. Okay, these 5 can run this host. It fits well, and there's a little bit of bin packing here, and do then the actual system level things to actually make it faster.
Yeah.
Okay, I think I get that level then. Cool. And so, all right, so we kind of get this sort of this lay cake built up now. We kind of understand from that point on. So I'm a Faasm. Maybe it'll be good to show maybe some example, right? What does Faasm even look like? And we can go from there. Yeah.
So why don't I share my screen and I can show you this. So Faasm, the other aim is to execute code that looks just like a normal application you would run on your, because this is sort of back to the original problem of what can I run on serverless nowadays? Not much unless I rewrite it. And so we were kind of trying to take relatively unmodified code and just run it. So hopefully these things will look somewhat like stuff that you're familiar with. So can you see my screen?
We can see it. Yep.
Great. So hang on. Let's see. Can you see that? Yeah, you can see that, right?
Yep. Yes.
Cool.
Micro KS. Yes.
Yeah. So basically, this is just showing what I was talking about earlier about a Faasm deployment. So this is just K9s. It's just an interface for looking at a Kubernetes cluster. These are the pods that run in the Kubernetes cluster to run Faasm. There's the top 4 are Faasm nodes, all running on different hosts. So there's 1 per host. And then there's a couple of other things for handling uploading of functions, sharing files, and a little bit of internal scheduler state, which lives in Redis, but not too much. So yeah, Minio is the sort of file sharing thing. Redis is for scheduler state, and upload is for handling function uploads. So then, yeah, this is just running on 5 standard cloud VMs. Like there's nothing fancy, all just standard Kubernetes stuff.
Cool. So
the first function that I'll go through a super basic function. This is just looking at the upload logs. So this function just says hello, basically. So it's C++, but it also we'll do a Python example in a second. So this is just a normal C++ executable.
Yeah, with the Faasm imports. Yeah, library.
But it imports a thing from Faasm.
Yeah.
And it sets the output, and that's pretty much it. So this, I've just say hello to him, and then we just compile this with the Faasm toolchain, which is just a modified WASI toolchain, basically. Like this is just compiling it with standard CMake, uploading it to Faasm, and then if we invoke it, we'll obviously get the message back. And that's basically the loop for running a Faasm application.
Wow, that's fast. Yeah.
Oh yeah, that's kind of, if it wasn't fast, I think that we would have failed.
Well, I guess because I think this is fascinating actually because you didn't upload anything. Well,
Oh, I did.
through you, I guess through the background, right? The
Yeah.
invoke is doing that. I guess, but from
Mm.
a typical point of view, in Kubernetes, you had to upload a Docker image. You got to do all this jazz,
Yeah.
and now you just simplify it to just one call. I think. So two things. Tell us why do you need to have a Faasm sort of like library to do even
Yes.
just outputs? Because why
Yes.
can't you just do echo? Like or
Yeah.
standard out, right? And what happens when you call invoke here? I think that's the magic a little bit, right?
Yeah.
We talked a
Yeah.
little bit about the sort of lower level placements,
Yeah.
but what is behind the scenes that is actually happening here?
So we can go back. Sorry, because this is recorded. I'll just skip back to seeing the code, which was about here. Cool. This is one of the fundamental problems that we've come onto later in the project. Is like, what is the programming model for serverless? How do I even write one of these programs? And I think a lot of serverless applications will look like this. They'll import something to do with AWS Lambda, Azure functions, whatever, to handle the input and output of the functions and return them to the user. So this is not the ideal state. This is the kind of entry-level function. We'll talk about programming models later and integration with something more intuitive. What this is just doing here is including this Faasm set output function. All that does is makes a call to the runtime on whatever host this thing is running and say, here's the output for my function. The Faasm runtime will then ensure that that makes it all the way back to the user who invoked the function. So what we'll see actually, we can also just capture the standard out of the function and return that too. You can write functions like that. You can just handle the normal argc, argv inputs to an application as well. And it's kind of just about exposing a generic API that could be built upon by, if you wanted to integrate another library into using Faasm, under the hood, it might have to make a few of those calls. So what I'm doing here is just showing the execution graph. So this is kind of where Faasm can tell you where it executed these functions. And obviously this, I'll just take this message ID and say to Faasm, tell me the graph of how this got executed. And obviously, because there was only one function executing once, it'll be a single node in the graph. And there we go. So all that's telling me is Faasm eventually executed the demo hello function on host 10.1.1.2.4.1.9.8, and it took 180 milliseconds, which is actually quite slow. So that's I would like that to be faster. I don't know why that was so slow in this instance. This comes on to what it's actually doing, of course. So when I say invoke, it's sending an HTTP request to a public endpoint. That actually just uses the normal Knative function forwarding thing. And that will eventually get forwarded to a Faasm runtime instance in the cluster. That Faasm runtime instance then says, have I seen this function before? If no, I'll see if any of my neighbors have seen it before. If one of them has seen it before, I'll just give the request to them and they'll do it. If no one's seen it before, I'll load the WebAssembly, parse the WebAssembly, load the machine code to do with it, and then execute it, then return the output to the user.
I see. So are you, because I don't know Knative intimately well, does Knative, when you send a request, the WebAssembly is already like compressed and uploaded at the same time?
So that was
as a payload, or?
Well, so actually there was two steps in this. We'll see it on the next one. I'll go through that in a bit more detail, the upload process. So I compile my code and then I upload it, then I invoke it. The compilation and upload step is just done in one go. So we can this is another very, very simple function just to kind of kick off the discussion. What this guy's doing is just echoing the input. So it's saying get the string input, print it. So on line 11, it's doing printf and echoing. And then on line 25, it's setting the output. So what Faasm will capture both the standard out from the function for you and give you the output. That works well. So sorry, this is you can see there it's compiled to WebAssembly as the first step, and then it's uploaded it. This user interface could definitely do with a little bit more work.
So the toolchain actually uploads to your share registry of it's like the Docker repository equivalent, right? Like I have all the functions. And
exactly.
Do you ID it based on your file name, I guess, in this case, or?
You just have a user, and so you would say upload Tim echo or Tim hello, and so then that means that it knows it has the concept of a user or a tenant, and they will have all their functions.
Got it.
All of your functions have the ability to talk to each other if they want. All of my functions have the ability to talk to my functions, but obviously they can't talk to each other. And so the runtime just segregates things based on user.
Okay. Right.
And so there we go. If we invoke it with no input, it just has nothing to echo.
Yeah.
We give it some input data, and obviously it'll tell us. There we go.
Awesome. Nice.
So that first line is the standard out, and the second line is the output of the function. The reason that you have to have a special output thing is that as soon as you've got more than one function operating, it becomes just having the standard out of that would be a mess. Like if I have a huge parallel thing of 100 functions, I need some way of distinguishing to say this is the output to the user. And if you have a long chain of functions, it might be the one at the end that wants to just put the output out, not the first one that you've invoked. And so this is sort of, as much as we want to execute applications transparently, there are bits where they have to be aware that they're in a serverless environment. So this is the Python equivalent, just saying hello, running, blah, blah, blah. So you can see this is just normal Python code. Again, we've had to import something from Faasm to write the output. I'll get onto that in a second. And so then this is a similar thing. Obviously, we don't have to compile the Python. We just upload the Python file. I'll talk about how we execute it in a sec.
Okay.
So you can see that that's just been uploaded to the same cluster, same endpoint, and then we just invoke it. And then it tells us what version of Python we're running. So Python can't be compiled to WebAssembly, so we can't offer the same guarantees if we just execute raw Python.
Yeah.
I can't safely execute your Python function and my Python function on the same operating system side by side. So what we do here is we compile the Python runtime to WebAssembly.
Oh, interesting.
And then use that to execute Python. So by definition, anything that the Python runtime executes is isolated with WebAssembly, but it's executing your Python code. It's interpreting the Python code that you give.
Interesting. So you basically took CPython and compiled that into Wasm?
Yeah.
Wow. Okay. Wow. So that's a beefy,
yeah,
a little bit beefier Wasm to load for sure, right?
Yeah, and CPython does a lot of stuff with the file system actually, to work out what modules are available, and the other really gnarly bit is that actually CPython will dynamically link. So a library like NumPy, for example, has a lot of C code in it.
That's right.
And it will dynamically link all that stuff at runtime. So that also has to be compiled to WebAssembly.
Wow. Okay.
So
you
NumPy.
have to do quite a lot actually to make.
Well, I can't take credit for this really. There's a really cool project called Pyodide, which is about executing Jupyter notebooks in a browser using WebAssembly. So they did a lot of heavy lifting to get that stuff compiled. I had to do a lot of work on top, but it would have taken me a hell of a lot longer without that project. Got it. So shout out to those guys.
Yeah, that's a really fascinating project as well. Yeah, well, I think we'll probably hopefully maybe dive into that a little later. But yeah, cool.
Yeah.
Okay, so we got the idea.
Cool.
You upload, and now we know this is Python. We know what is the right way to invoke it.
Yeah.
Interesting. So I think we get the gist of this Hello World versions, right?
Yeah.
We should probably go through a bit more, because the whole idea about this is about sharing resources and stuff.
Exactly.
Let me know, like, what is your next,
So the
we
next
have a sequence
thing,
of demos here. I think will be great to let's follow through this.
So the next guy is doing exactly that. It's saying, so all right, this is great. We can say a hello world, but what if we want to execute a parallel application that shares some data? Because this is kind of the difficult thing. And I've written a dummy application that just does a kind of, it's calculating pi by doing random guesses at points in a circle. So it turns out if you drop a load of random points in a square, the percentage of them that land within a circle that's a unit circle within that square can be used to estimate pi. And in theory, the more times you do it, the more accurate your estimation of pi is. It's nonsense. It's not a real stateful application, but it will show you kind of what's going on. Then we'll move on to a more complicated one. Okay. So we can skip the Python echo function, and then we'll get to, okay, so here's this is all in C++, which I apologize for. So what this function is doing is just each unit, which is this pi step function, calculating a random number, and then working out whether it fits in a unit circle. Then the key line is the one that says Faasm state append. Sorry, Faasm append state. What that's saying is, hey Faasm, just take my output and append it to this list of outputs from me and all my other functions that I'm calling pi. Then, oh yeah, there we go. This line is what I'm talking about. It's a bit gnarly because it's all C++. This could look a lot nicer if it was in Python or a different language. The major drawback of WebAssembly, of course, is that depends if you see it as a drawback. The most mature toolchain by a long way is the C and C++ toolchain. So this is kind of why we worked so hard on the Python support. Is people are like, I don't want to write serverless functions in C++. And you say, yeah, I get it. So we could do all of this stuff in Python, but it's been the latter half of the project has been working on big scientific applications, which I'll get onto in a sec, but they are written in C and C++. And so we focused on that. So we append the state. Basically, the idea is we have a load of these workers. They all append their state to this list in the sky. And then once they're done, the main guy says, I'm going to read all that appended state. So you can see there's a line where we dispatch all these chained calls where it says Faasm chain batch. Pi step is just the name of another function in this file. I'm not having to upload a separate serverless function to do this fan out. You have your main function. It just says, hey Faasm, I want to execute n instances of this other function in the same file. And then it just does it. So this is starting to look a little bit more like a normal parallel program that you'd write, where you would say, have threads. And you would just say, I want 10 threads to execute this function. And I want it just to work. Like, I don't want to have to say, provision another serverless function with another name. And then I don't want to have to call out some other HTTP endpoint to say invoke this. I just want it to look a lot like a multi-threaded function. You'll say, hey, but what about all this Faasm stuff? Good question. And later on, so we've implemented things like pthreads and Openmp to do multi-threading in C++. And that just works. Like you have your standard Openmp application, you compile it, and actually the threads themselves get invoked by Faasm, and it just does all the shared memory stuff under the hood.
I guess one question even to the PyStep, because PyStep, this is just pointing to like a symbol, right? In C, and obviously you can always change that, depending on how you compile it, or you change, the name.
Yeah.
That never always stayed the same. How do do you keep making sure that I can actually match? Hey, now I need to upload a new Wasm for that function now.
Yeah. So what's really nice about WebAssembly is that it gives you an execution state of your application, which is much simpler than if I was executing this on a standard full operating system. Basically, you can capture the execution state of a WebAssembly application by taking the stack pointer and then just an array of bytes, which is its memory. So the memory model of WebAssembly says the memory of my application is just a single linear array. And I can guarantee it will never do any accesses outside of that array, because that's how the format, that's how WebAssembly guarantees memory safety. For a runtime, that's great, because it means if I want to capture the whole state of my function and migrate it across hosts, I just need to copy that linear array and I need to get the stack pointer.
It will continue to just...
A couple of other things. Transplant it over here, then I can restart it. And so this is how we do threading as well. So if I invoke a new thread, it takes a snapshot of the main thread and copies that state over to other hosts, resumes them on the other host, and comes back.
Wow.
So WebAssembly, like
crazy state synchronizations, or like your coding had to be very, very tricky, you know, like
yeah. I mean, this became, do you know what? Actually, that part wasn't that hard to implement. The hardest part of all this to implement was probably getting all the system calls underneath to execute something like CPython to work and make sure that they're secure. Because ultimately, all these things are under the hood making quite a low-level system call to Faasm. And then we have to implement all of that. I can show you some of the code for that in a second. Because that's kind of gnarly, but this is basically doing this sort of silly distributed pi calculation that I was talking about. But it'll show you a little bit about this kind of fan out and scheduling idea.
Nice.
So we'll just upload this and then invoke it, which by default will run 4. What that's done under the hood is fanned out 4 more functions. They've done their little estimate and they've come back, and via Faasm state, they've just shared it. So then the execution graph should look like 1 node and then 4 others.
Awesome. Wow.
So that's how it worked.
Yeah. 13
and so then
19,
So then we can run it with some more. And this is where the execution graph gets a little bit useless. So if I say I want to run it with 50 functions, then it's run. And then if I look at the execution graph for that, it's going to look a lot bigger. But this is kind of the whole philosophy of serverless. It's like, I shouldn't care how big it is. And that's the graph for that. It's kind of a mess.
Awesome.
But you can see the nodes are colored based on which host they executed on. So there's some blue nodes, some yellow nodes, and then I think there's a green one right over there. So this is Faasm bin packing on the blue host, then the yellow host, and then you can see one had to get executed on the green host. So these are going a lot more speed. I'd like to see like 3 milliseconds or 7 milliseconds.
And so this is trying to like, so the optimization is probably looking like, hey, how do I get the read buffered sort of appendant state to be as close to be the same host as possible, so I can actually don't have to like read an increment and making sure everybody's doing the same, like
so there's
locking and stuff, right?
Yeah, this is what's kind of annoying about being a serverless provider, is that if I knew more about the functions, I could make better predictions about what stuff they're going to access and how long they're going to run for. But unfortunately, as a serverless provider, I treat everything as a black box because I can't do static analysis on your code. I could, but it would be quite difficult. So you don't know ahead of time whether it's going to be better to queue up all those tasks on a single host and just say that the efficiency gained from having that buffer on the same host?
Yeah.
Or do I have to start distributing them and then, worrying about locking and syncing state between different hosts? So this is just I'd say this is probably the final example we can look at that will get a bit more into some more funky stuff. So this is using Openmp, which is quite a difficult interface, program API to get your head around, just because it's written in C. But
it's dated, man. It's been a long time. I know.
Yeah, the core of Openmp is basically this pragma notation here. What I'm saying here is I want whatever comes in the curly brackets after this, I want to execute it in parallel with this number of threads, and then the final bit where it says reduction plus, that's saying after all said and done, I want whatever has been added to the result variable in my loop to be available in the result variable in the main thread when I'm finished. And there is actually a bug in our current implementation of this, which does mean I've had to put one line of custom code above it on line 25 that I've highlighted now. That is normally not there, but full disclosure. So in theory, you can take a totally unmodified Openmp application or any other multi-threaded application based on pthreads, and then you execute this. And this is doing exactly what I was saying we couldn't have before, which is where now, because I'm using a higher level programming framework that Faasm is aware of, Faasm can make better decisions about what it's doing. So Faasm can look at this code and say, oh, it's doing a parallel loop with this number of threads. So up front, I know how much parallelism it wants. And it's also doing a reduction on this result variable. So I know that I've got, that's more information, and that's great. And so we've also done an implementation of MPI, which is a kind of another annoying scientific C framework, but it's actually seeing quite a lot of use in deep learning frameworks now. So MPI is like the communication, you can use it as the communication layer. And this is sort of the level of abstraction that I think works. You pick quite low level, broad-based C, C++ APIs, and then you can build a Python application on top of that.
Got it.
But this for loop in the middle here is that kind of abstraction. So I could compile and execute this on my computer, and it would just run it multi-threaded, and this result thing just works. Then this line here where we're doing float pi equals 4 times float result, that's outside of the parallel section, and so that will get my thing. Behind the scenes, Faasm will say, okay, I'm going to execute the body of this loop on n machines, and then Faasm will then look at it knows here that the result is the thing that needs to change. But what Faasm actually does is a slightly more broad tracking of distributed shared memory. So what happens is if I'm executing a thread in Faasm on a remote host, Faasm starts executing that thread. It takes a snapshot of the memory using that linear WebAssembly memory thing I was talking about. And then it tracks which pages of memory have been written to by that thread on that host. Then once that batch of threads has finished executing on that host, it diffs the modified pages with the original, sends the changes back to the main host, which then merges the memory together. And so then to your main thread that's executing on the main host, once that parallel section is finished, it looks like it's got shared memory.
Single host. Interesting. Wow. And so
but
you have to really be knowing each one can only have subdivisions of, I'm only working on this chunk, right? I can't and do random changes because then I don't know the orders anymore, right?
So this is where actually multi-threaded programming generally doesn't actually give very strong consistency guarantees. Like when you write a multi-threaded application, you know that stuff can happen out of order. You know that stuff can trample on each other. So we make a guarantee that provided your multi-threaded application is free from data races and deadlocks and things, it will execute correctly. If it's not, then it's just like it would mess up on your machine, it'll mess up in Faasm, I guess. But the mess up in Faasm might be a little bit harder to debug because it'll look a bit stranger.
Really cryptic. Yeah. I guess
but
if
then
you can actually introduce like actual synchronization primitives, like maybe there's a little bit better. But obviously most people just do a single mutex, which is as worse.
Well, so Faasm does support all the other synchronization primitives like barriers and critical sections and things, but that gets incredibly expensive in a distributed scenario. Yeah. So actually, anyway, here this is just showing that it works.
Nice. Very
behind the scenes, that ran 30 threads in the background, and it was still quite quick.
30 threads is 30 invocations.
30.
You're gonna see a 30 graphs thing.
Yeah. I didn't actually run the graph. Sorry, this is now going on to the MPI version. This is just a slightly different programming model that does almost exactly the same thing. You can see here it's got a loop in the middle that does 2 random number generations, and then it calls MPI reduce. MPI is like a message passing framework. It doesn't rely on shared memory, but it does rely on a set of things running in lockstep and then sharing messages between each other, which makes it a very unserverless kind of framework, because you're saying to the provider, you have to give me this number of parallel units, otherwise my application won't work. And that's not very serverless. Usually you say, here's a function, run it at whatever scale it needs to, and this function is agnostic to that scale. Whereas MPI is a very different programming model, and it's actually a programming model that a lot of applications rely on. Like if I have an application where I have to partition data, I need to know what level of parallelism I'm getting. Otherwise, I can't do it efficiently. And this is one of the big drawbacks of serverless now, is that without being able to guarantee that level of parallelism, I can't do anything that useful. But the major downside to a provider is if I'm going to let people request a fixed level of parallelism from me, then that makes my job a hell of a lot harder, scheduling unpredictable batches of functions that might run for a very long time and take up space on my shared infrastructure. So the other thing that Faasm can do is live migrate functions. So if your function is running a bit too long, Faasm will live migrate it to another host where it might be better co-located with others. And also it'll preserve any kind of state or messaging that might happen between those functions.
Yeah, that's very fascinating, where it's traditionally been so hard to do, the crew live migration type of things, because you're actually doing the whole processes, right? Whole VM level, and it's just so hard to guarantee. But now it sounds like with Faasm, there's definitely nuances, but it seems like it's 10 times, 100 times much more easier to actually do this now.
I mean, it's a use case. Wasm gets you a lot of really nice. It simplifies the execution state of an application so much that you can start rethinking how you do this kind of cool stuff. So it's interesting.
And so I think this is super fascinating. I don't know how much we're able to get into Faasm like itself, but maybe tell us a bit more. Because we already talked about like the high level, but when it comes to actually executing, a function, you have the tool chains, the compilations. I guess that's probably too much, but more on the actual execution part. When I'm sharing resources, like what are you talked about a little bit like some of the hardest parts here. Maybe you can touch on like, okay, what are the things that are happening in the runtime that's executing the WASMs? What are the things you have to do to actually able to provide more support for sharing resources? And touch on maybe like the hardest parts you kind of have to figure out. Like you talk about CPython, what are actually some of the most challenging parts to make this work? Yeah,
so it's often like the most fun, interesting ideas aren't the most difficult to do. So the way the thing that Faasm does in order to allow things to share resources locally, specifically data locally, is that it takes that WebAssembly linear memory model. So you have 2 of your functions. They both have their byte array of bytes, which is their memory, and they're running. What Faasm does, it will if it knows that it's sharing a megabyte of data, shared state. It maps regions of those byte arrays onto shared memory that Faasm controls, so that actually both functions think they're still executing on a linear array of bytes, but actually pages of that is mapped to shared memory. And so therefore the functions can share memory. So that's not part of the WebAssembly security model, obviously.
That's right. Yeah.
We're breaking the isolation, but we're still preserving the isolation between those functions and anyone else they're not sharing stuff with. But we're sort of punching a hole in the isolation to let them share memory.
Interesting. So
however,
Wasm or whatever, Wasm time or stuff like that? Or?
No. So we use Wavm, WAVM, under the hood, which is another project that I have to give a shout out to, because that makes my life a hell of a lot easier. That executes WebAssembly as it needs to be executed. What Wavm doesn't do is provide any system call implementations that we use. It does provide a WASI implementation, and we use the WASI. I'm about to do a repeated. We use the WASI interface, even though the last I of WASI means interface. We use WASI to compile against, but then we actually have our own implementation of all the WASI functions to ensure that there's resource isolation between these things. Anyway, unfortunately, doing that shared memory thing is quite easy. In Linux, you just mremap pages, and then it just works. So that wasn't very hard. What was really hard was if I compile something like CPython to WebAssembly, the way WebAssembly deals with interactions with the underlying host, it just leaves an unresolved import. So I might let's say I have a system call like open, to open a file or something.
Yeah.
Unless my runtime provides an implementation of open,
that's right,
that WebAssembly will fail. So your runtime to execute a compiled WebAssembly function that makes a system call like that, your runtime has to provide an implementation for it. So if you run strace on CPython, you'll see it's doing like open, read, seek, all this stuff, and then it's doing some networking and all these things. Basically, every single one of those strace calls, we had to provide our own implementation and then think, how could that break the isolation between these functions? So then you can start by creating a chroot jail. It's just another Linux tool for creating a separate file system. Yeah. But then you have to make sure that has read-only access to all the Python file system, all the Python libraries that are on your shared file system, because you don't want to have to duplicate CPython, your whole library space for each function. So that was just like a really long slog that was quite boring, and it doesn't do anything funky. So that was probably the hardest part. Getting all those, so anytime you run strace on an application, it'll just print out all the system calls.
Yeah, all the calls you've done, yeah.
And for any WebAssembly runtime to execute an application, it has to provide an implementation of all those system calls, basically. And yeah, that's one of the drawbacks.
Handled by the Wasm runtime, I assume, is able to support all the syscalls, so that everybody needs to re-implement that for everyone, right?
So this is where Wasm, as a platform independent intermediate representation, leaves it up to that runtime. So like your Wasm runtime in your browser will not have implementations for a lot of those system calls.
Of course, yeah.
And you might get something like Wasm time or Wavm, one of these quite well developed out of browser WebAssembly runtimes, that might provide you a really nice WASI implementation. Unfortunately for us, because we're looking at a multi-tenant system, we need to then add another layer of security on every one of those to make sure that they're not going to break isolation between the functions. Because Wavm implicitly trusts the WebAssembly that you're using not to mess with other WebAssembly you're running, because why would you be running malicious WebAssembly on your machine, kind of thing. I guess it's that difference of like,
Okay, okay, I get it.
Faasm can deal with malicious WebAssembly,
Mm,
whereas Wavm or Wasm time doesn't make those guarantees in its implementation of
got it.
the
I see.
open syscall,
So
for example.
you kind of have to sit, I guess, below it, where you are
Yeah,
doing because you're having a multi-tenant model, trying to
yeah,
make it sure the performance is better.
yeah, yeah, yeah,
That's the whole goal. But that means you're gonna have to like do your own interceptions and do a lot more to
yeah.
either do the
It's
checkings or to at least give it a not just crash and burn when I don't even
yeah,
have that call, right? Like, hey, at least I return you something that can support this simple case, or even do
yeah, yeah,
redirecting, because this one looks good in this conditions. But that also, yeah, that's a really hard problem because there's so many corner cases you can never really like
yeah.
figure out. Like, yeah,
So then again, this kind of comes back to that stuff I was saying about serverless being a bit of get out of jail free card. You say, fortunately, serverless applications are simple, and so like we can kind of wiggle out of that and do a bit of hand waving and say like,
yeah. We shouldn't have
you
like
know,
a complete,
yeah,
crazy application that needs all kinds of stuff to be running, and yeah, that shouldn't be like the best suited cases for serverless in the first place.
yeah. So it's the other thing as well as like there's a problem in distributed systems research a lot of the time where people say,
Mm,
why can't I just run this application distributed?
mm,
And a lot of the time, it's just not written to be performant
yeah,
when it's distributed. And so we talk a lot about executing unmodified code and taking these existing APIs.
yeah,
But a lot of the time, something like a file system API, like I don't really, maybe I shouldn't be executing my heavily file system dependent application in serverless just because it doesn't really make sense in a distributed scenario.
yeah.
Um, and no one would, you'd probably sooner re-implement the library on top that
Mm,
makes those file system calls rather than try and implement the file system calls. And so this is where that boundary where we stop at like OpenMP, MPI,
yeah,
pthreads at the moment.
yeah. You
We
don't go
could
like
stop at like,
full
yeah,
Linux file system call VFS kind of things, right?
yeah, exactly. If you take it one level up, you sort of reduce the reach, but actually you make it a bit more convenient. I think there's a lot of interesting future work in serverless of like, for example, serverlessifying TensorFlow. Whereas if I have a TensorFlow application,
Yeah,
now I can target a CPU, a GPU, a TPU, whatever. What if one of those backends was serverless? And so actually TensorFlow will offload some stuff to serverless that works well on serverless.
interesting. Yeah,
But some people I think see this future of serverless as serverless is another device on which you can execute parts of your distributed application,
yeah,
but it's not all of it.
yeah, yeah.
And yeah, that's
So
we'll see.
I think we covered quite a lot, and
Yeah,
I'm sure there's
so
so much we can talk about, but just based on interest of time, I think just want to
yeah, yeah,
wrap
sure.
here. What is I think for last, where do we find your projects,
Yeah,
and do you hope people to contribute and use this? Like, what is the stage you're in? Like, what is the interest of the community that you're hoping for as well? Yeah.
yeah. I mean, it's at Faasm/Faasm, GitHub Faasm/Faasm, or just GitHub/Faasm, and it's it's been a research project, which means that, as you've seen from the last however long I've been talking for, there's a lot of like quite funky ideas in there, and it's written in C++. And so, if you're into hacking around with funky memory management and like distributed shared memory and all this stuff,
Yeah.
and you're interested in the cutting edge of serverless and distributed applications, then yeah, it's great. Like, I mean, there's a few of us working on it now. There's from different universities,
Mm-hmm.
all doing different research projects.
Got it. Yeah.
If you're looking for like an easy to use WebAssembly runtime, I
Mm-hmm.
would look at Wasm Time.
Yeah.
If you're looking for an easy to use off the shelf serverless product, I would use Knative and Kubernetes
Mm-hmm.
or OpenFAS. There's loads of really good, like really easy to use serverless projects. So I would say we're targeting, I'm being honest about the the level of complexity involved because it's doing some funky stuff, and it's certainly not production ready.
Yeah.
Um,
Yeah.
yeah,
Got it. Got it. But it's really fascinating that you're pushing the boundaries here, right? Like, what can we do with serverless? And
yeah,
I think until we really able to push more boundaries and finally figure out like, hey, what are the boundaries that are suitable?
mm,
A lot of things to make it easy to use actually isn't is technically feasible, right? It's just the
yeah,
amount of time and energy and just making knowing that this direction is actually good. That's actually a
yeah.
really hard problem in general. Yeah, yeah,
I mean, I still find cloud computing is difficult to use, even if you're using an off-the-shelf cloud computing product from your favorite cloud provider. Often there's quite a lot of plumbing that you have to do around that, and when it comes to scaling it out, auto scaling often works well, but then there'll be a point where it falls over. And I guess the idea behind serverless is motivated by people's desire to make things easier. So it will always be there, whether or not it's in its current form. I think increasing abstraction will always happen just because people get annoyed at